Well, hello again and welcome to our journey into algebra and number theory. This will be the last video in this particular section on the structure of UM and ZM. And we've seen now that U sub M is a cyclic group, I should say, when M is 2 for a power of an odd prime or twice the power of an odd prime. And if it's cyclic, it has at least one generator, which we've called a primitive root. And we're now going to look at some results to make it easier for us, firstly to find one primitive root and then to find all of them for a given modulus. So here's our lovely theorem here. If p is an odd prime and you take p minus 1 and you factorize it, where these are all primes, and if you can find a g so that g to the p minus 1 divided by qi is not 1 for each of the i's, then g is a primitive root. In other words, you're going to try and find a g, so you take this p minus 1 and you divide it by each of these primes and you check g to that power, and if it's not 1 for all of those, then g is a primitive root. So that narrows down, in fact, sometimes quite a lot, our search for primitive roots. You can look up this in more detail elsewhere, but it turns out that for a very large percentage of the time, 2 is a primitive root. If it's not, then 3 has even more chance of being a primitive root. And if both of those fail, which can happen, then 5 will almost certainly be a primitive root. And so you can normally find a primitive root just by checking the first few prime values. The second part says if g is a primitive root modulo prime p, then all the primitive roots are given by this set. That is, once you've got your primitive root g, you take any power that's relatively prime to p minus 1, and g to that power will give you another primitive root. And that, of course, agrees with what we saw before, that there are, in the case of p's prime, there are 5 p minus 1 primitive roots modulo p. Now, just to go through the proof quickly of this one, we're going to do the first part by looking at the contrapositive. That is, we're going to say that if g is not a primitive root, then I'm going to show that there is a q so that g to the p minus 1 on q is 1. So logically looking at not this implies not this, looking at the contrapositive. So we're going to suppose that g then is a primitive root, is not a primitive root, and g to the alpha is congruent to 1 modulo p, with alpha divides p minus 1. So we're going to write alpha then, we prime factorize it, as I mentioned before, where the bi's are less than the alpha i's, but the bi's and alpha i's are not all equal. So this one can be equal to this one, but not for all I. Otherwise, g would be a primitive root. So choose q sub j such that beta j is not equal to alpha j, and I'm going to call that q star. And I'm going to let gamma then be the difference between these two, which will not be 0. Now if we look at g to the alpha congruent to 1, then I can write the alpha then as p minus 1 divided by this product here. And of course, because this is 1, that tells me that this will be 1. If I raise both sides to these powers, then doing that we get some cancellation here, and we just end up with q to the p minus 1 on q star is 1 mod p, and that tells me we've found our value q so that g to the p minus 1 on q is 1 mod p for some q, and that's the negation of the original state. And that proves, by using the contrapositive, that proves the first part of the theorem. Part 2 I leave you as a little exercise. Well, just an example of how to find some primitive roots, find all the primitive roots, mod 13 and 17. So we take 13 minus 1 is 12, which I prime factorise to 2 squared be 3. Now, how do we find a primitive root? Well, you start at the beginning. You start at g equals 2, and you take this 12 and you divide it by each of the prime factors. So 12 divided by 2, 12 divided by 3, and we check 2 to that power. So 2 to the 6th turns out to be minus 1 modulo 13, and 2 to the 4th turns out to be 3 modulo 13, and therefore by our theorem 2 is a primitive root. We get all the primitive roots modulo 13 then by simply raising 2 to any power that is relatively prime to p minus 1, that is to 12. So 1, 5, 7 and 11. Calculate those, we get 2, 6, 11 and 7, and they are the 4 primitive roots modulo 13. For 17, we again, 17 minus 1 is 16, which is 2 to the 4th. It's only got one prime factor, and that's nice, so we only have to check one thing. So again, we start at the beginning, try 2. Well, divide 16 by 2 is 8, but when you work it out, 2 to the 8 is 1 modulo 17, so 2 is not a primitive root. So what do? Well, you try the next number. I go to 3, and I work out 3 to the 8, that is, 16 divided by 2 is 8. This one turns out to be minus 1 mod 17, and that tells me 3 is a primitive root. And the primitive roots then are given by, you take all the numbers that are relatively prime to 16, so that's 1, 3, 5, 7, 9, 11, 13 and 15, and when you calculate these modulo 17, these are the numbers you get: 3, 10, 5, 7, 11, 14, 7, 12 and 6. These are all primitive roots, these are all generators for Z17. Now, final little bit here is some applications back to some number theory and solving equations. And so I'm going to introduce this notion of an index or indices. These are just like logarithms. So definition: if g is a primitive root in um, if m is the right sort of number, then each element of a is expressible as some power of that. Well, we knew that. That's what we mean by being a generator. Every element is some power of our primitive root, and this k, this power, is called the index of a modulo m relative to g, and we're going to write this as k is the index of a to the base g, or relative to g. So these are just like logarithms essentially, but in this setting of u sub m. So for example, I take m to be 5, 2 happens to be a primitive root, and so I can write down the powers of 2, so I get 2, 4, 3, 1. So the index of 2 is 1, so you look at that number there, and there's its index up here. The index of 4 is 2, the index of 3 is 3, the index of 1 is 4, or you may as well take it to be 0, because 2 to the 0 also gives you 1. The interesting observation here, notice that this number is its own index. I'll say something about that in a moment, just observe it there. Now, a little theorem just to summarise the properties of this, just to show that it does behave exactly like a logarithm. So if g is a primitive root, a and b are in um, then the index of the product is the sum of the indices. Now we're now working upstairs, so we're working modulo 5m, not m anymore. So once we're working with indices, when we're working upstairs powers, we're working modulo 5m by Euler's theorem, which was a to the 5m is 1 modulo m, provided a and m are relatively prime. So just note that this is mod 5m, and again the other logarithm law, if you will, the index of a to the n, you can bring the n down the front, and that's congruent to that again modulo 5m. A little quick proof of this here. It's very simple. If the index of a is r, then that means a is g to the r. If the index of b is s, then b is g to the s. So multiply these together gives me this, and that just says the index of ab is r plus s, that's modulo 5m. Because we're working upstairs, we're working with the powers up here, everything works modulo 5m. and the r is just that index plus this one, and this part 2 follows by repeated application of part 1. So let me do an example now to show what we can do with these. So we can use indices to solve a range of congruence equations. So I'm going to work with the modulus 11. 2 happens to be a primitive root. So over here I've calculated the powers of 2, and I can make up a little index table. So for example, 2 to the 0 is 1, 2 to the 1 is 2, that's from here, so there's the number, there's its index. The index of 4 is 2, that brings me back to here. The index of 8 is 3, so 8 is 3. The index of 10 is 5, so 10 and 5, and so on. Notice again that there is a number which is equal to its own index. And if you do lots of examples of these, you'll find there is always at least one, or appears to be at least one number here, x, which is its own index. That problem is unsolved. We don't know whether that always happens. There's no counterexamples known, but there's no proof that it actually is true. There's another interesting problem. Seems a simple enough question, but nobody's been able to prove it. So once we've determined the primitive root, we omit the subscript. So here are just 4 little examples on how to use this to solve equations. This is a nice simple one. Firstly, I'm solving 8x is 7 mod 11. These are relatively prime, so I know it's got a unique solution, which we can solve by Euclid's algorithm, but here I'm going to do it using indices. So I take the indices of both sides, so I use the logarithm laws, that's the index of 8 plus the index of x is the index of 7, and I use my lookup table here to the index of 8 is 3 and the index of 7 was 7, and so I get 3 plus the index of x is 7. This is now mod 10, by the way, because we're working modulo phi of 11. I get the index, I can now solve that, the index of that of x is 4, and now I use the table again, so I look at 4 here, and it came from x is 5, and so x is 5 modulo 11. Just be careful with the moduli here, they skip from p to p minus 1. Second, more interesting example is to look at this one. I want to solve, or try and solve, x to the 5th is 8 mod 11. So again, I use the logarithm laws. I take the index of both sides and I can pull the 5 down the front, and the index of 8 is 3. Now, this is modulo 10 now, but now the GCD of 5 and 10 is 5, and that's not a factor of 3. So this has no solution. X to the 7 is 8 mod 11, same idea, take the indices of both sides, pull the 7 down the front, the index of 8 is 3. This is now modulo 10. Now I can get rid of the 7. What will I do there? I'm going to multiply both sides by 3. So 7 3s are 21, which is 1 mod 10, 3 3s are 9. Look back to the index table, if the index is 9, then the number it comes from is 6, so x is 6 mod 11. And finally, we look at 7 to the x is congruent to, this is now power the other way, so 7 to the x is congruent to 3 mod 11. You bring the x down the front, you get the index of 7 from the table is 7, index of 3 was 8, and that gives me 7x is 8 mod 10. And again, I can multiply both sides by 3. 3 7s are 1 mod 10. 8 3s 24, which is 4 mod 10. Now notice this gives me my x modulo 10, because x is a power. And so we'd expect x to be given modulo phi of 11, which is 10. And there's some examples of the applications of these primitive roots and indices. And that's the end of this particular section. In the next section we will move on to have a look at quadratic reciprocity.